So hello everyone, welcome to the last Jagiellonian seminar this semester, like Jagiellonian TCS seminar. Our guest today is António José Girão, or should I pronounce it differently?
No, that's fine, that's perfect. Yeah.
Yes, Antonio is known for his research in extremal combinatorics, probabilistic combinatorics, Ramsey theory. He did his PhD in Cambridge in 2018. The way how the result of Antonio, which I know best, is that degree boundedness is polynomial, and I believe he's going to tell us exactly about this topic today.
Yeah. Okay. So thank you very much for inviting me. It's very nice. Yeah. So I'll talk about how to find large induced C4-free subgraphs in graphs without large bi-cliques. Okay, which is essentially saying, okay. So let me, okay, the first thing I would like to start is how I approached, and Zach and other collaborators, this topic. Okay, so first I would like to mention is this conjecture of Thomas N from the 80s, which states the following. So for every graph, if the average degree is sufficiently large, then you can pass to a subgraph with high girth and still preserving many edges. So for every K and G, in the naturals, there exists some function depending on K and G, such that for every graph G, if the average degree of G is at least f of Kg, then there exists a subgraph G such that the girth of G is at least G, and the average degree of G is at least K. Okay, so this seems for me, it's a very natural problem. But unfortunately, we don't know essentially anything about this conjecture. So the only non-trivial, it's easy to pass to a bipartite graph and make sure that I delete all triangles, and I still preserve half of the edges. And the first non-trivial is how to delete C4. So the first non-trivial result is by Kuhn and Ostos. Let me mention this. So Kuhn, Ostos in 2000s, and they show that f of K, let me see the definition, 6 exists. So in other words, if the average degree of a graph is sufficiently high, then you can find a subgraph without triangles and C4s and C5s with still preserving high average degree. Okay. So, and this was a pretty long paper, I think, and it's a non-trivial result. So of course, okay, and that is, let me just say, that is all we know. So G greater or equal than 8, we don't know. So we have no idea how to get rid of C6s. And C4s are in some sense, I mean, it's harder than triangles, but in some sense, the C4 is looking at locally, you can look at like the common neighborhood and try to, and this is essentially how most of the proofs proceed, is essentially make sure that vertices don't have large common neighborhoods, and then some random procedure on the edges to delete C4s. Okay, but C6 sounds, you know, I thought a bit, and I think many people have thought, and it sounds, it's a very nice problem. Okay, but I don't think anyone has even some idea how to try to approach. So people were thinking, oh, what is this function fk6? So Is it polynomial in K? How does it behave? So let me state the conjecture, maybe, okay, more recent paper by Montgomery and Pokrovsky and Sudakov. So they showed, this is a theorem. So they show that f of kg is at most k to some constant k squared. Okay, so it's not, and I should say that Derek, so the Kuhn-Noss's result, this was like triple exponential in k. Okay, so now we know it's double exponential, it's not too bad, but of course the open problem, and I think.
So how is G involved in this bound here?
Sorry, G, I meant 6. Sorry,
6, yeah, it should be 6. Yeah.
Yeah, so essentially we just want to delete C4s. And the open problem is that if K6 is polynomial. Just big O K to the C for some C. Okay, and the lower bound, I think the best lower bound we have is K cubed. So, and I do believe this should be polynomial. I think it's to be a very nice result. Okay, so this seems a very interesting conjecture. And actually, there was an even older conjecture, very similar in taste, by Erdős and Heinel. So let me state it. I think from the 60s, which is essentially the same conjecture, but replacing average degree with chromatic number. So for every K and G, there exists some function, let's say H of Kg, such that, okay, maybe, yeah. For every graph G, with chromatic number at least H of Kg, there exists a subgraph such that the girth of G is at least G, and the chromatic number of G, sorry, prime, is at least K. Okay, so it's the same, essentially the same conjecture, but with chromatic number replaced, with average degree replaced by chromatic number. And here we know even less. So the only result we know is a very beautiful result by Rodels, which states that, okay, H so you can delete all triangles. And so every graph with sufficiently high chromatic number has a subgraph which is triangle free with high chromatic number. So H for K, sorry, opposite, HK4 exists. Okay, maybe at the end, if we have time, I can just say it. But then the bounds are just horrible. Yeah, I should say here the bounds are. I think they are power type essentially, but okay, maybe, no, but they are not good. Okay, so we don't know as well what happens if I want to avoid C4s, even not. I think it is quite hard to delete C4s and preserve chromatic number, but maybe even odd girth to be large. And I think this is also not known. So you could ask the same conjecture, but instead of saying girth, you say odd girth. And I think it would be very nice to at least delete C5s and triangles. Okay. So what else I wanted to say? Okay, so all of these conjectures have an induced counterpart. So I can ask the same thing, but in the induced setting. So induced versions. Okay, I think the induced version of Thomassen's conjecture is maybe less well advertised, but the other one was a big problem. So let me state it. So I think, okay, some people attribute to Espéret, some people say Rodel had asked, so I'm going to put Rodel plus Espéret problem. Okay, and the problem was the following. So is it true that if a graph with sufficiently high chromatic number must have either a large clique or a subgraph with preserving some chromatic number which is triangle free? So for every, let's say for every k chromatic number and m, there exists again some g of km, such that for every g with chromatic number at least g of km, either km is a subgraph of g, or there exists an induced subgraph of g where the chromatic number of g is at least k, and g prime is triangle free. Okay. Unfortunately, this is false. So the induced version is incorrect. I mean, okay, so we couldn't just ask for an induced with high chromatic number without triangles, because the graph could itself be a huge clique. So we need to avoid some substructure. Okay, it seems natural that, okay, you avoid a small clique, but this is false. So this is a very nice result of Carbonero, Hump, Moore, Sperkel, where they show that, okay, for every m, there exists a graph G, which is K for free. The chromatic number of G is at least m, and for every induced subgraph of G with chromatic number greater or equal than 5 implies G prime has a triangle. So yeah, one can cook up graphs with arbitrarily high chromatic number such that any induced subgraph with chromatic number 5 greater or equal to 5 must have a triangle. Okay, so this conjecture is false, at least for k. So this conjecture is false, at least for k4 or something. Good. Okay, so we know that this is false, and this was generalized in a very beautiful way by Briansky, Davis, Bartos. So they show the following. They show that for every clique k, there exists some constant, such that for every m, there exists a graph where the chromatic number is at least m, g is k plus 1 free, and for every induced subgraph with chromatic number at least this constant implies G prime contains a KK. Okay, so it's the conjecture is false is very, very false. Good, and this result actually allow them to solve. I mean, essentially, this result allow them to resolve another problem of Espéret on the big chromatic chi-boundedness families. Okay, so let me. Yeah, so I don't want to say too much more about this induced version, especially of the first conjecture, but you can just think what would be the correct thing to avoid, which is the large complete bipartite graph. So is it true that for every k and g and s, there exists some f of k, g, and s, such that if the average degree is sufficiently large, then I can find an induced subgraph, and your graph is KSS3, then you can find an induced subgraph with high girth and high average degree. And I don't know, so I tried to use this construction of or similar constructions to the chromatic number in this setting, and I could not disprove this conjecture. So maybe, of course, we don't even know the non-induced version, but maybe the induced version could be true in this case. So yeah, induced is true. Okay, I don't know. I don't think many people have thought about that. Oh, and okay, so now let me state some. I mean, probably most people know, but I'll state it anyway. Okay, so so what I want to say is the following. So now, so definition, so a class of graphs H is hereditary if for every H in the class and for every subgraph, induced subgraph implies that H prime is in our class, okay? And we say H is chi-bounded if okay, there exists some F such that for every H in our family, the chromatic number of H is bounded by the F of the clique number. That's right. Okay, so chi-bounded families, I'm not at all a specialist in this topic, and I'm sure everyone who's listening knows much more about this type of problems. I should say is that I don't think we know essentially, we don't have many characterizations of which hereditary class are chi-bounded. And we don't even know if the class of graphs avoiding a tree is chi-bounded. This is a conjecture of some Garford and Sumner, I believe. So yeah, and okay, so given this definition, you know, for example, for paths, we know paths are, so the class of graphs without path of length k is chi-bounded. But for example, the function, we don't know if that function is polynomial. So it was a very nice problem asking, can we find a class of graphs which is chi-bounded but not polynomial chi-bounded, meaning that this function f cannot be taken as a polynomial. Okay, and these same people, so Briansky, Davies, and Malczak, they actually show that essentially for every f there exists, okay, which grows a bit, some can have to grow slightly. It's not too bad, but has to have some lower bound on how it grows. But so there exists a class, there exists some class of graphs for which okay, so H is chi-bounded, and the chi-bounding function is f. Okay, so there are, so in some sense, this function can grow as fast as we want. Okay. Now, okay, so let's see what I'm interested in this talk is about, I'm interested to talk about degree bounded. Okay, so I heard this from Rose. I mean, we were always thinking about given a graph without complete bipartite, how can you find a large induced subgraph, which is C4-free and has high average degree? But okay, Rose told me in this terminology, and I thought, okay, it is a nice way to put it. So we say that the class, let's say again, H is degree bounded if again, a hereditary class is degree bounded if there exists some G such that for every graph in H, the average degree of H is bounded by a function of the largest complete bipartite, balanced complete. Oh, sorry. Oops. Yeah, which I denote by tau of H. Okay, so let me just say tau of H. This is just the maximum S for which KSS is a subgraph. This is not induced, subgraph of H. Okay, and the class of graphs is degree bounded if the average degree is bounded by a function of the largest complete bipartite. Okay, so what sort of classes do we know are degree bounded? Okay, so one type of classes is, for example, for any tree, the class of E-free graphs is degree bounded. Okay, so let's actually try to prove this. Okay, so let's assume. Okay, so let me try to prove, give a very short proof of this. Proof. Okay. We are going to assume, and I'll explain why we can. We have some G, which is C4-free. The average degree of G is at least, say, 100 times the size of the tree. Okay, and I'll explain at the end why we can assume C4-free. Okay, so what can we do? Okay, so we can pass to first a subgraph of G where the minimum degree of G prime is at least 50 times the size of the tree. And now we can just try to, let's say our tree here is some, let's say, okay, it's this tree. So we try, here is our graph G prime, has large minimum degree, and it's C4-free. Okay, now we try to embed. Okay, so we pick a vertex, let's say this is X1. Okay, just choose any guy. Okay, and suppose that at some point we have already embedded an induced copy of a subtree. Okay, now I need to embed, so I look at where this guy is. This guy is here. Now I need to embed this one. Okay, so I look at the neighbors of this one outside the tree. Okay, this has at most t vertices and the minimum degree is 50t, so I have many outside. Okay, so now pick a vertex outside and we can say, okay, let's, I don't want to just copy the same picture, but okay, for every vertex that I've already embedded, how many neighbors can I have inside the neighborhood of this? Let's call this maybe Z. And because the graph is C4-free, I can have at most 2 neighbors. Okay, so for every guy, I have at most 2 neighbors in the common neighbor. Okay, a bigger picture. So this is Z, This is the neighborhood, and this is the tree I've already embedded. And for every guy here, I can have at most 2 neighbors. Okay, but then I don't choose this, I don't choose that, I don't choose any of these neighbors. So I deleted at most 2t. So there's a vertex here, which is a neighbor of these, and which is not a neighbor of any of the guys I've embedded so far. Okay, so then I can continue. And then just, yeah. Okay, so this shows that if it's C4-free, so in some sense, embedding structures, induced structures in C4-free graphs is much simpler than in KSS-free. So if there was a way to assume that, okay, if I don't have a KSS, I can find an induced subgraph without a C4, then everything becomes much easier to embed my structures. Okay, so, and now here let me say, I believe, not 100% sure, but I believe the McCarthy, Rose, and maybe plus some small lemma from a paper of Letzter, Kwan, maybe Butchich and Sudakov. But anyway, so I think Rose essentially observed that it is true that so for every K and S, so there exists some F of K and S, such that for every graph G, which is KSS free, okay, KSS free, I don't mean induced copy of KSS, I mean no KSS. I know that usually the terminology is induced, but okay, so maybe okay, maybe I'll write no KSS. And the average degree of G is at least F of KS, implies that I can find G prime induced C4 free, again, no C4, and the average degree G prime to be at least K. Okay, so then I can assume that our graph is C4 free. I start with any graph with high enough. So I look at what is the largest by click. If the average degree is much, much larger, then I can pass to a subgraph with high chromatic number, and which is C4, which doesn't contain a C4. And then I can embed. Okay, so this, yeah, was a nice, I think, so Rose essentially proved this for when the graph I start is bipartite, and this extra lemma allows you to actually pass to an induced bipartite with high average degree. Okay, let's not go into this. And now, so what do I want to say? Maybe I should say that this result was originally proved by Kirstein and Penrice. So what other class of graphs are degree bounded? Okay, so T-free graphs are degree bounded. Another class is, for example, so for every H, for every graph H, the class of H3, sorry, class of graphs without an induced subdivision. H is also degree bounded. Okay, and this was proved by Kuhn and Ostas. And again, the bound is bound on tau, and H is like maybe 4 exponential power of height 4. Okay, so a natural conjecture was to show that okay, for every H and S. There exists
So
some
do you
polynomial.
forbid, so do you forbid here H itself as well as an induced subgraph, or
Yeah, and any induced subdivision.
okay, an induced
Yeah.
subgraph. I see. Okay.
But yeah, I mean, even if you say the class without a large induced subdivision, this is also degree bound. So yeah.
Okay.
So the conjecture was that for, okay, fix any graph, you fix some S, and then there's a polynomial that just depends on okay, maybe, sorry. So for every H, there exists some polynomial that just depends on H, such that for every graph G, if the average degree is at least P of H times tau of G, implies an induced subdivision of H in G. Okay. So now we know this is true. So two groups of authors have proved it. So maybe let me state, so theorem. Okay, so Burnoff. Maybe I should, maybe there's a new here, sorry, apologies. Lucic. Of Lucic, Davies, Cook, sorry. And okay, and I mean, we proved this slightly more general thing, so they show the conjecture is true. Okay. What other degree bounded? And then this is essentially where my knowledge about degree bounded class of graphs stops. So I asked Rose if she knew some. She told me about, yeah, some other, but I'm not so familiar. But maybe, so let me just say, for example, one thing that, okay, I immediately tried to think about, which was, okay, is this true for chi-boundedness? So is it true that the class of graphs without an induced subdivision of some graph H is chi-bounded, and this is false? So these two parameters are not, it's not clear, they are not so comparable. Good, okay. So what do I want to say? So maybe now let me state then our result. So theorem is that every degree bounded class of graphs is polynomially degree bounded. Exact
Hereditary class of graphs, right?
Sorry?
You mean hereditary, like
everything. Yeah, sorry.
okay, that's like part of the definition of degree bounded,
Yes.
I guess. Okay, thanks.
Yeah, sorry. Please do interrupt because I forget many little things that are important. Okay, so every degree bounded hereditary class of graphs is polynomial degree bounded. So very much in opposition to what happens in the chromatic number case. So let me, okay, the proof is not, okay, the proof evolved in the following way. I think this is more interesting to say. So first, me, Zach, Alex, and had some ideas on how to improve this bound of rows.
So Antonio, is there some universal degree of this for this polynomial, or?
Yeah. So okay, let me maybe I can state it. So we show that F, you can take always F to be, let's say F of S, where S is the largest by click, is at most, okay, maybe some large constant depending on the class. Sorry, H, let's say this is class H. And then you have S to the, I think it's H maybe to the fourth. Again, some big O of these. Yeah, so it's just, so I didn't explain what is, yeah, so this is just where CH is just the maximum D, such that the average degree is D, and G is in our class, and G is C for free.
Okay.
Yeah. So you look at C for free graphs in your class, look at the highest average degree, and then the function is just a polynomial on that, and yeah, it's not something terrible. It's even like that thing to the power 4. So yeah. Okay, and then again, this is another very different thing because, okay, in chi-bounded, we know that it's not enough to look at it's not enough to look at triangle-free graphs and know if they are, if the chromatic number is bounded or A for free or etc. But in degree-bounded, it's enough to look at, to test whether a degree-bounded hereditary class is degree, sorry, to test whether a class of graph is degree bounded, is enough to look at the C for free, and if we know this is bounded, then we know the class is degree bounded. Okay. So what I was going to mention now is the following. So the main so how it evolved. Yeah. So we had me, Alex, and Zach had some. We improved this. So the bound that Rose had here was again triple exponential or something. Okay, and we knew we had the first paper where we used some combining some arguments to actually reduce to single exponential. Okay, and then me and Zach continued thinking, and then we realized that actually we could, I mean, introducing some new techniques, we could reduce it. Okay, so let me.
May I have a question?
Yes.
You said that in Rose's result, it was important to look at bipartite
Yes.
graphs. Is there bipartiteness involved in this statement here?
No. Yeah. So
okay, so here, for instance, in the definition of CH, it is irrelevant whether G is bipartite or not. You just require that it's C for free.
Yeah.
Okay, thanks.
So we don't have any. Yeah. This is the. Yeah. Any degree bounded is polynomial degree bounded, and the function is. Yeah. There's no bipartiteness thing. I mean, it's a natural. It's a natural barrier in the methods that this bipartite comes, because it's much easier to find complete bipartite, or if I know that already the graph has this bipartite structure. But we have this dichotomy. So I'll tell something about the proof and we'll see. Okay. But I wanted just to mention how this, at some point we realized that this is quite similar in some sense to this Erdős-Heinel conjecture. So maybe just, okay, I'm sure everyone knows, but in any case, okay. So Erdős-Heinel conjecture. This is a lovely conjecture. Okay, so for every H, there exists some constant, such that for every G without, which is H free, okay, H induced free, implies that G, alpha of G is at least n CH, or the click number of G is at least n to the CH. Okay. And so we don't know. I think we are still far from knowing if this is true. But in the last couple of years, we had lots of results. And so now we know that paths essentially satisfy the Scheinel conjecture. We know another huge class that are prime, so cannot be built from smaller blocks that satisfy the Scheinel. We know C5, we know P5, which were like some barrier of our understanding. But I still think we are quite far from. Maybe Alex and Paul disagree. I don't know, but yeah. Anyway, but there was one interesting result by Fox and Sudakov, which I like to mention, which is like a one-sided version of the Scheinel conjecture. So they prove the following: that okay, if you give me a graph H, there exists some CH, such that for every G, either H is an induced copy G, or the independence number of G is at least n to the CH, or there is a K, N, CH, and CH. So this is a complete, so either you have your induced copy, or the independence number is huge, or you find not a clique, but a complete bipartite. It's a one-sided version of Erdo-Scheinel, because okay, one part is instead of saying a clique is relaxed to having a complete bipartite. Right. So what we realized, and actually the proof of the other authors realizes the same things. It's interesting to observe that. So we realized the following: that under the assumption that our graph H was bipartite, then we could prove essentially this result with much better dependencies, but even dropping this by an average degree condition. Okay, so let me state that. So we prove that for every H, and I would say this is, I don't know if this is the main ingredient, but this was definitely, when we realized this, what unblocked, because we knew already how to clean the graph. Yeah, maybe I'll save it for later. So for every bipartite, for every H bipartite, okay, there exists some constant, and this constant is also like not too bad. It's like 1 over, can be taken to be like 1 over 100 H squared or something. Such that for every graph G without induced H, either two of the following things happen. So, sorry, I should say with average degree. Let's say G. For every graph G with n vertices without an induced copy of H, an average degree at least n to the 1 minus epsilon H, and again epsilon can be like 1 over the max degree of H, or 100, whatever. And then, so if you fix your favorite bipartite graph, if I give you a graph, then and I tell you the average degree is polynomially, I mean, it's a polynomially smaller from the complete, but still polynomially small, and doesn't contain this induced copy of H, then it must have a large complete bipartite. Okay, so this implies that easily, because if you have independence number smaller than some small polynomial in N, then you must have high average degree by Turan. Okay, so this implies that by Turans, because we know that any graph with average degree D contains an independence number of size at least N over D. Okay, so we get this. Of course, they prove for every H, and we prove for H bipartite, but H bipartite, I mean, every graph, I mean, essentially what we were trying is to find a subdivision. So every graph has like the one subdivision of a graph is a bipartite graph. So we can always assume, at least in our main first goal was to prove this conjecture, the polynomial D. So we could always assume the graph we want to avoid is bipartite, because it's the one subdivision of the graph we wanted to avoid. Good. Okay. So maybe I'll give a sketch of this, because it's not. I think the hard part is to realize that it could be true, and then I don't think it's so. So let me give a sketch of this. So, okay. So the first thing I want to say is the following: since the average degree of J is at least n to the 1 minus epsilon, this implies that I can find some set A, where the size of A is at least square root n, and the degree of X is at least n to the 9 over 10 for every X in A. Okay, so we can find some set which is polynomially big. Every guy sends n to the 9 over 10 neighbors. Okay, so this is the first. So this is just by counting. If you have a high average degree, you must have many vertices with high degree. Okay, and then the second thing is that dependent random choice. Okay, for those who don't know, it's just saying the following. If a graph is has many edges, then so we see, okay, we know that for any fixed bipartite graph, we know the Turan number is polynomially small. So we know that for any fixed bipartite graph, we know the maximum number of edges without containing this copy is n to the 2 minus some epsilon, depending on. Okay, but if you have dependent random choice, essentially, or in the way we are going to apply, is essentially says if you have much more, then you must have many of these copies intersecting in some way. Is roughly, but so this allows us to find some subsets of A. So here was A. We now find a subset where, okay, the size of A is still large, say 1/4, and every delta of H, recall that we fix some bipartite H. Every delta of H vertices in A prime have n to the 2/3 common neighbor. Okay, so I find here some subset A prime, such that every single set of size delta of H, let's say maximum degree, let's say it's 10. So every set of size 10 has many common neighbors. Okay. So these are the two first reductions. And then, okay, so here is now we forget everything but H. Sorry, but A prime. Now let's see, this is the rest. Okay, so now what we are going to show is that if you take at random, let's say our H, it looks like this. So it's a set of size A vertices here, B vertices here, okay, some edges. And the maximum degree of H is delta. Okay, so now we are going to embed this part here. And we are going to embed these guys greedily in the following way. So take a random set. Okay, so uniformly at random. Uniformly random set of A prime of size A. Okay. So take some A guys in this A prime. And now what we want? We want to say that for any set S, okay, and let's say, so for we want to prove that for every S inside, let's say these are labeled 1 up to A. So for every subset of 1 up to A, and let's define YS is the set of Y's in the vertex set of our original graph, such that the neighborhood of xi, such that y is in neighborhood of xi if and only if I is in S. So it's just saying the following. It's just saying that you have your guys 1 up to A, you fix some subset, and then when I take at random, I ask, what is the size of those vertices which connect to exactly that subset? Okay, and so we want to prove that for any subset, this random variable, so or the size of this random variable, ys, is large. Okay? And if this is large, then I can, let's say with high probability, for every s, ys, which is that, the size of ys is large. And then if this is large, then I can just greedily embed. So, okay, you tell me I want a vertex which is a neighbor of these two and none of the others. Okay, so I choose S to be 1, 2. So I know there's many guys for which they connect to exactly those and none the others, and so on. And obviously, I have to assume that S is at most delta, because I never need to add more delta neighbors. This is crucial. Okay. So let's try to see why is that. Okay, so first, maybe let's just say, okay, we may assume S is 1 up to L. Okay, so you fix some L smaller than delta. I mean, whatever, all of these variables behave exactly the same. It's irrelevant where they are in the set, in your random set. So just say, I want a vertex connected to first L guys and none to the others. Okay. Now, we know already that we can find many vertices which are connected to these L guys, but maybe they are connected to the others. We don't know. So let's define YLT, okay, to be those guys, Y, again, in the vertex set of a graph, such that Y is a neighborhood of X. Sorry, X is maybe I should say, so the first vertex, I call it X1, that I take at random. The second is X2 and so on. So we are going to take X1 up to XA random vertices. Okay, and I define the random variable YTL to be those guys in the vertex set, such that Y is a neighbor of XI for all I smaller or equal than T. So this is for all equal than T, and now, yeah, good. And for some T, and T is something between L and A. So what is it saying? If and only if. Okay, it's just saying that, maybe a picture is good. So it's just saying that, okay, suppose that your S is just the set 1, 2, 3. Maybe, okay, maybe 1, 2, 3, 4. Okay, so now I say so Y of 4 is just, it's just how many guys are connected to the first 4. So this is just those y's for which they are a neighbor of those first four. And we know there's a lot. Okay, but what is y5 is, okay, is those guys which are connected to these, but not to this. And what is I6 is those that are connected to these first four, but not to the fifth and the sixth. Okay, and now, so we want to, why are we doing this in a chain? Because we want to say, okay, provided that YTL is large, YT plus 1L is going to be very large with very high probability because of the following. So suppose that I fix some T. So I have the first four guys which I want to know the common neighborhood, and these guys are not joined to any of these. Okay, but now this guy is a random vertex, okay? And I'm going to assume this YTL, the size of this is large. Now, how many vertices can I have in my graph which have a large neighborhood to this YTL? So let's see, what is the size of those y's in my vertex set such that the neighborhood of y intersection YTL, this size is at least 1 minus 1 over, let's say, S, 10S times the size of YTL. So how many vertices can I have which send all but at most a proportion of 1 over 10S? Recall what is little s. Little s is the largest clique, by clique. Sorry, maybe. So we assume, so G is KSS free. Good, okay. And you can't have many vertices because, I mean, but just by pigeonhole, if I can't have more than S guys because this guy is connected to all but at most a 1 over 10 S proportion. This guy is connected to all but a 1 over 10 proportion. So after S times, they are all connected to a set of size at least half. And then you would have your size. And yeah, so provided this is large, then you'll find your KSS. Maybe yeah, I know we are essentially done because the point is just the following, is to say that there can't be many guys with a very, very large common neighborhood. Okay, so the probability that the next guy is going to be chosen from this very bad set, so this is at most S, but this is huge. Recall, this is like S to the constant depending on our bipartite. So the probability is really, really small. Okay, so if I choose some guy outside, then why am I good? Because I know this has at least 1 over 10S times YTL proportion of non-neighbors by definition of, so if let's say this is set L and this is L. So any vertex outside L has at least 1 over 10S non-neighbors. 2 non-neighbors to YTL. Okay. So then the probability that YT plus 1L is not at least a 1 over 10S proportion of YTL. So the probability, just write that YT plus 1L, sorry, the size of this is smaller than the size of YTL over 10S, well, is at most, is only if I choose a guy in this bad set L, so it's L over the size of A star, or A prime. Recall that I'm taking vertices from A prime at random. Okay, but if A prime is huge and L is very small, this probability is extremely small. So even if I do it 8 times, I have that the probability that my last guy, which is AL, is at least what I started with, which is n to the, so every S guys, sorry, every delta guys have a large common neighborhood of size at least n to the 2/3. So I have like probably this is not n to the 2/3 over, and in every step I drop by a factor of 10s, and now I do it at most 8 times. So the probability this is smaller than this, well, it's at most n to the, well, okay, now sometimes it's nice to say that the graph has size n. S is just a polynomially small. So this is like the product over I1 up to A of 1 minus n to the minus 1/3 or something, because this probability is going to be like smaller than n to the minus 1/3. Okay, so this probability is extremely small. So the probability, sorry, exactly the opposite. Sorry. So the probability, the last one is very small, is at most that in some step you went very small, but so this is at most the sum over 1 up to A of the probability in that step I was bad, which is at most n to the minus 1/3. Okay, so this is at most 8 times n to the minus 1/3, but this is very small. Okay, so then with high probability, I can find, not with, yeah. So with high probability, I can find a set of size A such that, and then I take the union bound. Yeah, so how many sets of size delta I have S, choose delta. But okay, this is at most 2 to the A, and we know that 2 to the A times n to the minus 1/3 is still very, very small. Because S is like, n is like S to the A squared or something. Good, okay, so now we just need to show that this is going to be an independent set. Okay, and now we estimate what is the probability that if you take a set of size A is an independent set, and if the probability is slightly bigger than this probability, then both happen, and then I'm home essentially. I think the argument of the other groups, so Bernoff and Bucic, Cook and Davis, is slightly, I think it's slightly simpler in a way, but yeah, I mean, at some point, I think Zach is very interested in the constants. So yeah, I think their constants are worse. So found this way that gives slightly better quantitative results. Good. Okay. Maybe I should stop and maybe say something about yeah. So let me just state this conjecture. But I would like is that this conjecture to be false in some sense. So I'd like a construction. So here is the problem. Let's say. So can you construct a, for every D and some S, a graph G, which is KSS with no KSS, and average degree of G is at least D, such that every induced subgraph of G, which is saying C6 free, has average degree small. Okay, maybe okay. Can you construct for every D? Maybe okay. Let me put the quantifiers correct. Can we construct? Or maybe is there some K and some S such that for every D there is a graph G with no KSS with high average degree, such that every induced subgraph with average degree at least K must have a C6. And this would be if this is true, or if these graphs exist, then this would be the natural equivalent to these graphs with high chromatic number, such that every induced subgraph with bounded clique number and every induced subgraph with high chromatic number must have a triangle. Yeah. Okay, so I stop here.